Hello friends and welcome. Today I am going to deliver a lecture on concept of exchange energy, relative energies of atomic orbitals and anomalous electronic configurations. Let us first try to have a look at the main objectives of today's deliberation. Number first, to give a general and thorough idea about the concept of exchange energy. Number second, explaining in detail the concept of atomic orbitals. Number third, to discuss relative energies of atomic orbitals, and finally we shall be discussing the anomalous electronic configurations. Now we will start with the introduction about the concept of exchange energy. Exchange energy is the energy released when two or more electrons with the same spin exchange their positions in the degenerate orbitals of a subshell. The exchange interaction is a quantum mechanical effect that only occurs between identical particles. Despite sometimes being called an exchange force in analogy to classical force, it is not a true force as it lacks a force carrier. The effect is due to the wave function of indistinguishable particles being subject to exchange symmetry, that is, either remaining unchanged or changing its sign when two particles are exchanged. Both bosons and fermions can experience the exchange interaction. For fermions, it is sometimes called Pauli repulsion and related to the Pauli exclusion principle. For bosons, the exchange interaction takes the form of an effective attraction that causes identical particles to be found closer together, as in Bose-Einstein condensation. The exchange interaction alters the expectation value of the distance when the wave functions of two or more indistinguishable particles overlap. It increases for fermions or decreases for bosons the expectation value of the distance between identical particles. Among other consequences, the exchange interaction is responsible for ferromagnetism and for the volume of matter. It has no classical analogy. Exchange interaction effects were discovered independently by physicists Werner Heisenberg and Paul Dirac in 1926. The exchange interaction is sometimes called the exchange force. However, it is not a true force and should not be confused with the exchange forces produced by the exchange of force carriers, such as the electromagnetic force produced between two electrons by the exchange of a photon, or the strong force between two quarks produced by the exchange of a gluon. Although sometimes erroneously described as a force, the exchange interaction is a purely quantum mechanical effect unlike other forces. Now, let us discuss exchange of spatial coordinates. Taking a hydrogen molecule-like system that is one with two electrons, we may attempt to model the state of each electron by first assuming the electrons behave independently and taking wave functions in position space of phi a r1 for the first electron and phi b r2 for the second electron. We assume that phi a and phi b are orthogonal and that each corresponds to an energy eigenstate of its electron. Now, we may construct a wave function for the overall system in position space by using an antisymmetric combination of the product wave functions in the position space. Psi a r1 vector r2 vector is equal to 1 divided by under root of 2 psi a r1 vector phi r2 vector minus phi b r1 vector phi a r2 vector. Alternatively, we may also construct the overall position space wave function by using a symmetric combination of the product wave functions in position space, that is, phi s r1 vector r2 vector is equal to 1 divided by under root of 2 phi a r1 vector into phi b r2 vector plus phi b multiplied by r1 vector phi a r2 vector. Treating the exchange interaction in the hydrogen molecule by the perturbation method, the overall Hamiltonian is H is equal to H0 plus H1, where H0 is equal to H square divided by 2m phi 1 square plus phi 2 square minus E square divided by R1 minus E square divided by R2, and H1 is equal to E square divided by RAB plus E square divided by R12 minus E square divided by RA1 minus E square divided by RB2. Two eigenvalues for the system energy are found, that is E plus minus is equal to E0 plus C plus minus JEX divided by 1 plus minus B square, where the E plus is the spatially symmetric solution and E minus is the spatially antisymmetric solution. A variational calculation yields similar results. H can be diagonalized by using the position space functions given by equations first and second. In equation third, C is the Coulomb integral, B is the overlap integral, and JEX is the exchange integral. Now, coming to the limitations of the Heisenberg Hamiltonian. Because the Heisenberg Hamiltonian presumes the electrons involved in the exchange coupling are localized in the context of Hitler-London or valence bond theory of chemical bonding, it is an adequate model for explaining the magnetic properties of electrically insulating narrowband ionic and covalent non-molecular solids, where this picture of the bonding is reasonable. Now, let us discuss the next part of our today's lecture, that is atomic orbitals and relative energies of atomic orbitals. In quantum mechanics, an atomic orbital is a mathematical function that describes the wave-like behavior of either one electron or a pair of electrons in an atom. This function can be used to calculate the probability of finding any electron of an atom in any specific region around the atom's nucleus. The term atomic orbital may also refer to the physical region or space where the electron can be calculated to be present as defined by the particular mathematical form of the orbital. Each orbital in an atom is characterized by a unique set of values of the three quantum numbers, that is n, L and m, which respectively correspond to the electron's energy, angular momentum and an angular momentum vector component, that is the magnetic quantum number. Each such orbital can be occupied by a maximum of 2 electrons, each with its own spin quantum number s. The simple names s orbital, p orbital, d orbital and f orbital refer to orbitals with angular momentum quantum number L is equal to 0, 1, 2 and 3 respectively. These names together with the values of n are used to describe the electron configuration of atoms. With the development of quantum mechanics and experimental findings such as the two-slit diffraction of electrons, it was found that the orbiting electrons around a nucleus could not be fully described as particles, but needed to be explained by the wave-particle duality. In this sense, the electrons have the following properties. First, the wave-like properties. The electrons do not orbit the nucleus in the sense of a planet orbiting the sun, but instead exist as standing waves. The lowest possible energy an electron can take is therefore analogous to the fundamental frequency of a wave on a string. Higher energy states are then similar to harmonics of the fundamental frequency. Second, the electrons are never in a single point location, although the probability of interacting with the electron at a single point can be found from the wave function of the electron. Now, coming to the particle-like properties. First, there is always an integer number of electrons orbiting the nucleus. Second, electrons jump between orbitals in a particle-like fashion. For example, if a single photon strikes the electrons, only a single electron changes states in the response to the photon. Number third, the electrons retain particle-like properties such as each wave state has the same electrical charge as the electron particle. Each wave state has a single discrete spin, that is spin up or spin down. This can depend upon its superposition. Now, let us discuss the types of orbitals. Atomic orbitals can be hydrogen-like orbitals, which are exact solutions to the Schrodinger equation for a hydrogen-like atom, that is, an atom with one electron. Alternatively, atomic orbitals refer to functions that depend on the coordinates of one electron, that is orbitals, but are used as starting points for approximating wave functions that depend on the simultaneous coordinates of all the electrons in an atom or molecule. The coordinate systems chosen for atomic orbitals are usually spherical coordinates, that is r, theta and phi in atoms, and Cartesians, that is x, y and z in polyatomic molecules. The advantage of spherical coordinates for atoms is that an orbital wave function is a product of three factors, each dependent on a single coordinate. Phi r, theta and phi is equal to r r, theta theta and phi phi. The angular factors of atomic orbitals, that is theta and phi, generate SPD functions as real combinations of spherical harmonics, that is YLM theta phi, where L and M are quantum numbers. There are typically three mathematical forms for the radial functions R, which can be chosen as a starting point for the calculation of the properties of atoms and molecules with many electrons. That is, the hydrogen-like atomic orbitals are derived from the exact solution of the Schrodinger equation for one electron and a nucleus for a hydrogen-like atom. Number second, the Slater type orbital is a form without radial nodes, but decays from the nucleus as does a hydrogen-like orbital. And number third, the form of the Gaussian type orbital has no radial nodes and decays as e raised power minus distance squared. Now, let us discuss the next part of our today's lecture, that is orbital energy. In atoms with a single electron, that is hydrogen-like atoms, the energy of an orbital and consequently of any electrons in the orbital is determined exclusively by n. The n is equal to 1 orbital has the lowest possible energy in the atom. Each successively higher value of n has a higher level of energy, but the difference decreases as n increases. For high n, the level of energy becomes so high that the electron can easily escape from the atom. In single electron atoms, all levels with different L within a given n are to a good approximation degenerate and have the same energy. This approximation is broken by a slight extent by the effect of the magnetic field of the nucleus and by quantum electrodynamic effects. The latter induces tiny binding energy differences, especially for s electrons that go nearer the nucleus, since these feel a very slightly different nuclear charge even in one electron atoms. In atoms with multiple electrons, the energy of an electron depends not only on the intrinsic properties of its orbital, but also on its interactions with the other electrons. These interactions depend on the detail of its spatial probability distribution, and so the energy levels of orbitals depend not only on n but also on L. Higher values of L are associated with higher values of energy. For instance, the 2p state is higher than the 2s state. When L is equal to 2, the increase in energy of the orbital becomes so large as to push the energy of orbital above the energy of the s orbital in the next higher shell. When L is equal to 3, the energy is pushed into the shell 2 steps higher. The filling of the 3d orbitals does not occur until the 4s orbitals have been filled. The increase in energy for subshells of increasing angular momentum in larger atoms is due to electron-electron interaction effects, and it is specifically related to the ability of low angular momentum electrons to penetrate more effectively towards the nucleus, where they are subject to less screening from the charge of intervening electrons. Now, let us describe multi-electron atoms. In these atoms, the energy of orbitals have the same values of n but different values of L. Thus, both the values of n and L determine the energy of an orbital. The following hold good for multi-electron atoms. Number first, different orbitals having the same principal quantum number n may have different energies. Number second, for a particular main energy level, the orbital having higher value of the azimuthal quantum number L has higher energy. When n is greater than 3, some orbitals belonging to a lower main energy level may have higher energy than some orbitals belonging to the higher main energy levels. The orbital having lower n plus 1 value has lower energy. Now, let us discuss the last part of our today's lecture, that is anomalous electronic configurations. In atomic physics and quantum chemistry, the electron configuration is the distribution of electrons of an atom or molecule in atomic or molecular orbitals. For example, the electron configuration of the neon atom is 1s2, 2s2, 2p6. Electronic configurations describe electrons as each moving independently in an orbital in an average field created by all other orbitals. Mathematically, configurations are described by Slater determinants or configuration state functions. According to the laws of quantum mechanics, for systems with only one electron, an energy is associated with each electron configuration, and upon certain conditions, electrons are able to move from one configuration to another by the emission or absorption of a quantum of energy in the form of a photon. Knowledge of the electron configuration of different atoms is useful in understanding the structure of the periodic table of elements. The concept is also useful for describing the chemical bonds that hold atoms together. In bulk materials, the same idea helps us explain the peculiar properties of lasers and semiconductors. Now, let us describe Aufbau principle and Madelung rule. The Aufbau principle was an important part of Bohr's original concept of electron configuration. It may be stated as: a maximum of 2 electrons are put into orbitals in the order of increasing orbital energy. That is, the lowest energy orbitals are filled before electrons are placed in higher energy orbitals. The principle works very well for the ground states of the atoms for the first 18 elements, then decreasingly well for the following 100 elements. The modern form of the Aufbau principle describes an order of orbital energies given by Madelung's rule. This rule was first stated by Charles Janet in 1929, rediscovered by Erwin Madelung in 1936, and later given a theoretical justification by V.M. Likovsky. Orbitals are filled in the order of increasing n plus L. While two orbitals have the same values of n plus L, they are filled in order of increasing n. This gives the following order for filling the orbitals, that is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, 8s, 5g, 6f, 7d, 8p and 9s. Now, at last coming to the applications. The most widespread application of electron configurations is in the rationalization of chemical properties in both inorganic and organic chemistry. In effect, electron configurations along with some simplified form of molecular orbital theory have become the modern equivalent of the valence concept describing the number and type of chemical bonds that an atom can be expected to form. This approach is taken further in computational chemistry, which typically attempts to make quantitative estimates of chemical properties. For many years, most such calculations relied upon the linear combination of atomic orbitals approximation using an ever larger and more complex basis set of atomic orbitals as the starting point. The last step in such a calculation is the assignment of electrons among the molecular orbitals according to the Aufbau principle. A fundamental application of electron configurations is in the interpretation of atomic spectra. In this case, it is necessary to supplement the electron configuration with one or more term symbols which describe the different energy levels available to an atom. That is all about today's lecture. Hope you have understood it very well. Thank you very much and goodbye.